Alright, let's start by talking about the concept of linear relationships. It's common for numerical variables to have linear relationships between them. But what does this mean? Well, that when one variable changes, so does the other. They covariate. And this relationship is commonly visualized with a scatter plot. So let's look at an example. Let's say we have data on the ad spend and site traffic per week for a certain company. We can see if a relationship exists between these variables by plotting them in a scatter plot. And what this does is that it takes each pair of values and plots it in a point on the graph. So the point on the far right here represents week 5, and it lives at the intersection between the ad spend value in the x-axis, which in this case is $72,954, and the site traffic value along the y-axis, which is 7,592 here. And if we look at all of these points together, then the linear relationship is pretty easy to see. As ad spend moves up or down, then so does site traffic, making it a positive relationship. Now, there are two types of possible linear relationships between variables. They can either be positive or negative. Now, we just saw this example of a positive relationship in which as one variable changes, then the other changes in the same direction. This is an example of a negative relationship though, and in this case, as one changes, then the other changes in the opposite direction. So the higher the digital ad spend, then the lower the offline ad spend, which makes sense. So those are the two types of linear relationships, but it's also possible for variables to have no relationship. So if we plot the digital ad spend and the load time, then we won't find any association between them. In other words, the variation in one of these variables has nothing to do with the variation in the other. Now, let's jump to Excel and create a scatter plot ourselves to see if we can find a relationship between two of the variables in our project. Here in the Excel statistics workbook, I'm going to scroll over to the regression analysis section and go through the first link. And what we want to know is if a student's MBA grade is related to their undergrad grade, which seems like a reasonable assumption to make. So let's create a scatter plot. We just need to select both variables. And then go to Insert. You'll find the scatter plot icon here, and then just select the scatter plot. Now let me quickly make some formatting updates here. Let's remove the title. Let's add some axis titles instead. So this is the undergrad grade. The variable on the left will always be plotted on the x-axis. This is the MBA grade. Let's make these nice and bold so they pop out. And then I'm going to adjust my axis limits here so that I can see this relationship more clearly. We know that the grades go from 60 to 100, so let's change it to that. 60 to 100. And 60 to 100. And I'm just going to change the color of the dots here. We can make them orange instead. And let me remove the shape outline. So our scatter plot is looking nice here, but does a relationship exist between these two variables? Does a change in the undergrad grade seem to indicate a change in the MBA grade? Not really, right? At least not for this generation of students. So doesn't look like we'd be safe to assume that a linear relationship exists between these two variables, which is a shame because we maybe could have used the undergrad grade to predict the MBA grade. Alright, now that we know how to visually identify linear relationships, it's time to talk about the correlation, which is a numerical measure of the strength and direction of a linear relationship. So the correlation can be any value between -1 and 1, in which -1 indicates a perfect negative correlation, 0 indicates no correlation, and 1 indicates a perfect positive correlation. So the further away from 0, the stronger the relationship, with the sign simply stating if the relationship is positive or negative. Now, let's look at the same examples from the previous lecture and calculate their correlation, which is denoted by R. The first value of 0.858 indicates a strong positive correlation. The second value of -0.499 indicates a moderate negative correlation. And this makes sense if you think about it. You can see that the scatter plot on the left feels tighter, while the scatter plot in the middle here does follow a linear trend, but is a bit more spread out. And finally, this value of 0.008 indicates no correlation. So even if we didn't have these scatter plots here for reference, these correlation values would give us the same information. Now, pro tip, use the Correl or Pearson functions to calculate the correlation between variables in Excel. I'm not really sure why there are two. Technically, there are different types of correlation coefficients, the most common of which is the Pearson correlation coefficient, hence the name of the formula, but both of these actually calculate the Pearson correlation, so you can use either one. But before I go to Excel and show you how to do this, I want to talk about the subject of correlation and causation. Again, correlation between variables simply means that there is a linear relationship between them. But causation goes one step further and means that changes in one variable cause the changes in the other variable. So while causation does require correlation, correlation does not imply that there is causation. And let's look at an example. This is a scatter plot of the number of ice cream cones sold in a country per week and the number of drowning deaths in that country in the same week. So these two variables are clearly correlated. But do ice cream cones cause people to drown? Do drowning deaths cause a surge in ice cream sales? Of course not. And this is important because, like these, there are many variables that display linear relationships without having causal relationships. This can either be by random chance or because there is a third hidden variable that affects both, in this case likely the average temperature. So as we continue to explore linear relationships and even start using them to make predictions, always keep in mind that correlation does not imply causation, and that variables can be related without causing a change in one another. So it's important to use your logic, and in many cases subject matter expertise, to determine whether a causal relationship is possible or at least reasonable to assume. So with that said, let's jump to Excel and look at an example with our project. I'm going to jump to the correlation link under regression analysis, and you'll see that we're going to explore the same question that we just did visually, but see if we can use the correlation coefficient to come to the same conclusion. Now, keep in mind that in this case, it wouldn't be crazy to assume that higher undergrad grades cause higher MBA grades. But it would be crazy to think about it the other way around, since you can't get an MBA degree if you don't have an undergrad degree to begin with. So let's calculate the correlation here. I'm going to use the Correl function. And you can select the arrays in any order that you'd like. I'm going to start with undergrad degree and then do the MBA grade. You'll see that we get a result of 0.1, and let me just use the Pearson formula to show you that we'd get the same result. Again, correlation of 0.1061. So what does this mean? Well, it essentially indicates that there is no correlation here. Even if it is slightly positive, it's mostly really close to 0. I think as a rule of thumb, anything around 0.5 or negative 0.5 can be considered moderate, and anything closer to or above 0.8 or negative 0.8 can be considered strong. Again, you can always just check the scatter plot and use both of these to come to a reasonable conclusion. In this case, that no correlation exists between the undergrad grade and the MBA grade. Alright, time for our first assignment of the section. We just got another email from Nick Normal on student salaries, so let's see what he has to say. I was wondering if there's something we can do to estimate the potential salaries for the students that haven't gotten jobs yet. Could you check if the annual salaries for our placed graduates have any relationship with the other data that we have on them? If so, any way you could visualize it for me. Okay, so key objectives here. Number 1, to calculate the correlation between annual salary and each of the other numerical variables. And number 2, to create a scatter plot to visualize the relationship for the variables with the highest correlation. Good luck. Alright, time for an assignment on simple linear regression. Let's read Nick's email. By now we know that our program improves student employability scores by 50 on average, but could there be another variable that explains by how much we can expect each individual student to improve by? Because that would be huge. So, key objectives here. 1, calculate the correlation between employability improvement and any relevant numerical variables. Number 2, create a scatter plot to visualize the relationship for the variables with the highest correlation. And number 3, if applicable, build a regression model to predict employability improvement. Alright, time for the most important lecture of the section on the fundamentals of regression. The goal of regression is to predict a dependent variable using related independent variables. Which makes sense. If a linear relationship exists between two variables, well then you can use the value of one of them to predict the value of the other. And this is achieved by fitting a line through the sample data points that essentially models the population. So let's take a look at the same example and try to predict site traffic based on advertising spend. Which is logical, as bringing in traffic to the site is one of the main goals of advertising. So we have this scatter plot, which we already know shows a strong positive relationship. And in this case, the ad spend is the independent variable, also known as X, which is what we're going to use to help us predict the dependent variable, which is site traffic, or Y. Now, this scatterplot represents the sample of 52 weeks of data. But if we wanted to make predictions about the population using regression, well then we put a line through it. And this line is a model that can be used to predict site traffic in a given month based on the advertising budget, which is super valuable to us. Now, important call out, it isn't recommended to predict values outside of the range of the sample, as this relationship that you're seeing here isn't guaranteed to continue. We can predict site traffic for ad spend amounts between $30,000 and $80,000, but we don't know if this same model will apply to spending of $200,000 or $500,000, for example. It could very well hit a point of diminishing returns somewhere after this, and then the site traffic would eventually even out. So for prediction, let's stick to this region here. But let's talk a little more about this line though, otherwise known as the linear regression model. The linear regression model is actually an equation that best describes a linear relationship. And if you remember from math class, the equation that describes a line is y equals mx plus b. But if you're studying statistics and apparently everything needs to be in Greek, then the equation is that y hat is equal to beta 0 plus beta 1 times x, which is the same thing as mx plus b, which represents the line. Now in this equation, beta 0 is the y-intercept, or the value for y when x is equal to 0. Even if you have no advertising budget, for example, you are bound to have some site traffic, even if it's minimal. Now beta 1 is the slope, or size of the relationship, and this is frequently referred to as rise over run. So for every unit that I increase my independent variable by, how many units does my dependent variable change by? If that number is large relative to 1, well then the size of the relationship is large. And the sign indicates if it's a positive or negative relationship. In this case, we're looking at a positive relationship. Now, x is the value for the independent variable, which we will plug into our model to obtain the predicted value for the dependent variable, or y hat. And this point here represents the predicted value of y at x in our model. Now, you will also see the linear regression model represented this way, because remember, this line is simply the one that best fit through the sample points, but they aren't all going to live along that line. So y here is the real value for the dependent variable at x, like we can see here, which means that we need to add an error or residual caused by the difference between the real and the predicted values, which is going to be represented by this distance that you can see here. And this is important because the error is what's actually used to find the line that best fits through the point, which is ultimately our regression model. And this is accomplished using a method known as least squared error. So again, the least squared error method finds the line that best fits through the sample points, and it works by squaring the residuals or errors, adding them up, and then minimizing that sum. And it's important to know this because squaring the residuals removes the negatives, but it also gives more weight to outliers since their error is larger. So you can keep them if you want them considered in the model, or you can remove those outliers once you've identified them if you don't want to include them. Now, let's take a look at how this works. Let's say that we have these x and y variables and we visualize them in a scatter plot. If we want to use x to predict y, well then we just put a line through the points, right? Now, you may be seeing this line and thinking, whoa, that makes no sense. Why would you draw it there? In other words, why would you just predict 30 across the board? Well, I'll have you know that 30 is the mean value for y, which is what we've been using as our best guess for this entire course. So this should really open your eyes to how powerful and useful regression is. Now that I made my point though, let's try a better line. So if we plug our x values through this regression equation, then we get these predicted y values, which have these errors compared to the real y values. And if we square those errors and then add them up, well then we get the sum of the squared errors, which in this case is 862.5. Alright, cool. Now let's try another line and see if we can get a lower value than that. So let's move this, we get this new model here, and now we get a sum of squared error of 722, which is better. And we could continue to do this and move this line until we find the least square error, which in this case is actually very close to this model here, but you won't ever actually go through this trial and error process yourself. Tools like Excel or Python or R do this in less than a second. The idea here was just to get you to A, understand that regression is really just a line meant to model the sample points and make predictions, that B, the line is described by an equation with these components, known as the linear regression model, and that C, the best line, is found by minimizing the sum of the square error, like we saw here. And that's all just based on the distance between the points in your sample and the line that represents your model. So now that we understand all that, we can try it out in Excel ourselves. Here in Excel, I'm going to go to the regression analysis section and click on the linear regression link. And we want to see, is a student's employability score after graduating related to their score before graduating? And if so, can we model that relationship? You'll see that I've already gone ahead and calculated the correlation, which is very strong and positive at 0.94. And I already created the scatter plot as well, with before as the independent variable and after as the dependent variable. And again, you can see a very strong visual relationship between the two. So how do we find the line that best fits through these points? Well, all we need to do is right click and add a trend line. It's that easy. And we can even scroll down and add the equation for that line as well. Close this. Move this down here. So what does this mean? Well, if we look at the slope, which is also known as the coefficient, it's very close to 1. It's 1.03. So that means that we can infer that for every 1 point that a student gets above the average before the program, then they're going to get 1 point above the average after the program. And we just need to add 41.63 on top of that. And if you think about it, it's confirming what we pretty much knew already. Want to predict employability scores after the program? Well, then take the employability score before and add 50. This is just saying multiply it by 1.03 instead and then just add 41.63, but it's going to get you a very similar number. So not the most useful regression model here based on the size of this relationship, which is close to 1, but it does illustrate how these models work and how quickly we can create them in Excel. Okay, so we just saw how to create a regression model using a scatter plot in Excel, but you can also use Excel functions. So these Excel functions help make calculations related to linear regression. You have the correl function, which returns the coefficient of correlation. We saw this one already. You also have the intercept function, which returns the y-intercept from a linear regression given a dependent and independent variable. So you feed it the y and x values from your sample, and it returns the intercept from the regression equation. And then you have the slope function, which returns the slope or the coefficient for that same regression. So you can use those two functions to generate the regression model, and then just multiply an x value times the slope and add the intercept, and you get your predicted y value. Or you can use the forecast function, which does the same thing. You give it an x value to use as the predictor, and then the y and x values from your sample. It uses those to build the regression model, plugs in the x value, and then returns the prediction. It really is that simple once you've confirmed that the linear relationship does exist between the variables. And finally, we have the RSQ function, which returns the coefficient of determination, or R squared, and the stakes function, which returns the standard error. Now, I'm not going to get into those now since we'll cover them once we talk about evaluating the regression model, but I will leave them here for reference. So now that we know about these, let's go to Excel and use them. Here in Excel, I'm going to go to the Prediction with Excel's Regression Functions link. And you'll see that we have the same scenario, so we're trying to predict employability scores after the program by using the employability scores before the program. We have our correlation, we have our regression model and our equation by using the scatter plot, but now let's use Excel functions instead. So for the y-intercept of our regression model, we can use the intercept function. And it's important to feed it the y's first, so the dependent variable, which in this case is the employability after, and then the x values. We get 41.63, which is this right here. And for the slope, we can use the slope function. Again, known y's, known x's, and we get 1.0326, which is this right here, exactly. So if we wanted to make a prediction, let's say, what will be the employability after for a student that got 200 on his employability before? Well, we can grab this, which is the x value, multiplied by the slope or coefficient for that x value, and then just add the y-intercept. And we get a prediction of 248.1. Or we can replace this with the forecast function. Now, the simple forecast function is available for earlier compatibility. You can use this. It does use a linear regression model. Or you can use the forecast linear, which is the same thing. I'm going to use this one. My X value to predict for is this one right here. These are my Y's. These are my X's. And again, I get 248.1. And we can continue to predict for any value in this range. So 105, 380. And we get our prediction, which is roughly our before plus 50, which is what we were using before. But we could send this to Tommy Test as well, so that he can use this slightly, maybe, more accurate model. And that's simple linear regression in Excel for you.